Let's take a quick look at the differentiator circuit in both the time domain and the frequency domain. The differentiator circuit involves having Z1, the resistor connected to the source, being replaced with a capacitor. So the impedance here at Z1 is 1 over Cs. But let's look first at the time domain from the time domain perspective here. The output voltage is just going to be 0, then going in the direction of current flow. The output voltage is going to be, is going to equal negative R times I. Well, I is just the current through the capacitor, and the current through the capacitor is equal to C dV dt. The voltage across the capacitor is just Vn of t. So we have then I is equal to C times the derivative of the input voltage with respect to time. So V out then is equal to negative R times C times the derivative of the input voltage with respect to time. So sure enough, the output is proportional to the derivative of the input, and it's a differentiator circuit. Now, from the frequency domain perspective, we've got the transfer function T of S is just equal to Z2 negative, keep forgetting the negative Z2, which is R, divided by Z1, which is 1 over Cs. So that turns out to be simply negative R times C times S. Now we can look at the frequency response, T of j omega, which of course is just this thing evaluated at S equals j omega, so that's going to be equal to negative RC times j omega. The magnitude of the transfer function is equal to RC omega, and the phase is equal to negative j, the phase of j omega is equal to negative j or negative 90 degrees. Once again, let's look at what happens at omega equals 0. At omega equals 0, the magnitude of the transfer function is just 0. T of j omega equals 0, and as omega approaches infinity, the magnitude of the transfer function also approaches infinity. From a practical perspective, differentiation accentuates changes in the signal. If the signal is tainted with noise, the differentiator circuit amplifies the noise and limits its usefulness in many applications. Under those circumstances, where you do actually want to use it, they will typically place a relatively small resistor in series with a capacitor to limit the current spikes resulting from the differentiation of the noise. The Bode plot is just again just a straight line. It's increasing as omega linearly with omega. Once again, it's got a positive slope, or not once again, it now has a positive slope with a slope of 6 dB per octave, or again 20 dB per decade. The unity gain frequency is the frequency where the magnitude of the transfer function equals 0, which of course would be omega equaling 1 over C times R.